All right, let's take a look at our lesson for today, which is on the dot product and some applications that have to do with vectors. So before this lesson, we got some experience with vectors from an algebraic point of view, where we learned how to add and subtract. The operations that we dealt with in this lesson were adding and subtracting vectors and, normalizing them, doing some different things, finding their components. The lesson before, we worked on the geometric, representation of a vector, how they look, how you would position them to add them. So we've done a few things with vectors. Today what we're going to do is something different. We're going to do another kind of operation on vectors, which is called a dot product. So a dot product is, and I'll look right here. So it's this little u dot v. That's what the dot product is, like this u dot v business. All right, that's the dot product. And so how do you do the dot product? So if you have a vector, vector u has the components a1, b1, and let's say vector v has the components a2, b2. So what you do to do it's a operation or a process that we do with vectors. What you would do is you would match up your x components. You would take these two and then you would multiply them. Then you would match up the y components and you would multiply them together. And then the result of this process is actually going to be it's not going to be a vector, it's actually going to be a number or a scalar. That's the result of a dot product. The dot product is going to give you a number. So that's the mechanics of what we do, how we do a dot product. There are two types of things we're going to do with dot products. One of them is finding the angle between two vectors. So that's this scenario down here where we're finding the angle between two vectors. The formula that we use for that is got a dot product in it. It's this cosine theta of u dot v over magnitude of u times magnitude of v. So that's one use of the dot product is in this formula itself. So when we are finding the angle between two vectors, we need to be cautious and make sure that these vectors are tail to tail. The vectors have to be placed tail to tail. For example, here's a vector and let's say, that's a vector. Okay. So these are tail to tail. This would be the angle between the two vectors, the theta. So that's one significant thing. They need to be tail to tail. But if the vector is in standard form, so let's say the vector is in standard form, it's just got the x component and the y component. This is called standard form. If the vector is in standard form like these components, then it is in it's tail to tail. It's in standard form. So this would be like our vector u, perhaps that's our vector v, and theta would be what we'd be finding with this formula, the angle between them. So if our vectors are in standard form, it's very easy. Standard form, that's just a reminder, these vectors begin at 0, 0. They begin at the origin. That's where standard form vectors begin. So if they're in standard form, that's great. These vectors will be tail to tail and we don't have anything to worry about whatsoever. Okay, so I'm going to pause there for a second. So this is what the vectors look like when they're tail to tail. And if we have the vector in component form, it's just automatically in, it starts at the origin, so they will be tail to tail. Okay. So the second thing we're going to be doing with the dot product is using the dot product to determine if two vectors are orthogonal. Orthogonal means perpendicular. Okay, so orthogonal or perpendicular. So we can determine if two vectors are perpendicular to each other by simply doing the dot product and getting a 0. If we do the dot product and get a 0, then vector v and vector u are perpendicular. And I'm going to use the symbol that we used in geometry for perpendicular. Okay, so then the vectors will be perpendicular if their dot product is 0. Now that's talking about the dot product. What I would like to do is go back up to the very first bullet and talk about the horizontal and vertical components of a vector. So we've already done that in previous lessons. I just want to highlight it a little bit more. And this form right here, so let's look at this form. This form is called component form. So that part is called component form, and this part is called I and J form. And remember, they need their little hats. They're really excited about their little hats. I and J form. So if we want to write a vector in component form or I and J form, there are these handy little formulas which we really don't have to memorize. A is talking about the x component, and B is talking about the y component, but we don't have to memorize those formulas in order to find, what the components are. I'm just going to remind you of what we have done in the past. So if we have a vector like this, and let's say this angle is 45 degrees, and we just want to find the x and the y. X vertical and, horizontal. X is horizontal, y is vertical. So if we want to find the x and y component of that vector, we could just use trig, right? To find the x component, we would say cosine of 45 degrees equals, and let's say this length is, 4. Cosine of 45 degrees equals adjacent, which is x, over hypotenuse, which is 4. And so you can look and compare that to this formula right here. So compare this formula to this. And they're exactly the same. The magnitude of the vector was 4. I made that a 4. Let's get rid of that. So this is the same as this. So you don't have to memorize that formula. We've already been doing that before. I just wanted to show you the formulas that they, talk about. Again, we don't have to memorize them because we know how to just use right triangle trig to find our vertical and horizontal components. And this is just the formula written in IJ form. That's all. The x component, that's the x component with the I, and that's the y component with the j. Okay, so I'm going to pause here for just a moment. Let me just pause for just a moment. Are there any questions so far? So we see that we're going to use the dot product in two different scenarios. One is inside a formula, finding the angle between two vectors, and the other is to determine if two vectors are perpendicular. This dot product theorem that's sitting right here, this dot product theorem, is just a different way. So if you look at this formula is just a different version of that formula being written out. We really don't ever use the formula written out like that, like the dot product theorem is telling us, u dot v equals magnitude of u times magnitude of v times cosine of theta. we normally use it to find the angle between, which is the one that I've highlighted in green. But I just want you to notice they're the same thing. They're the same formula. They're just solved for different variables. Okay, but we are going to utilize this one down here. The cosine one is the way we're going to use the dot product theorem. Okay. Good? Okay, so let's go to our examples. Find the direction of the vector. Okay, we've done this before. Find the direction of the vector. And this is just regular, so this is regular trig. Regular trig direction. There are three different kinds of direction. The first kind is, we're just going to put a 1 by it. This is three different kinds of direction. The regular trig and direction. And what I mean by that is there's no context. We're not talking about bearings or north, south, east, west. None of that's going on. It's just a regular old problem where what we're going to do is what I would do is I would graph this. And for some students, it's easier to put this into component form. In component form, this would be negative root 3, 1, where negative root 3 is my x component because it's in front of the I, and 1 is my y component because it's in front of the j. So when I graph this particular vector, I'm going to go left, negative, so it's negative root 3, and up 1. So this is where my vector is. It's in the second quadrant. Okay, and so my direction, since this is regular trig direction, what we do is we start at the x-axis and we rotate counterclockwise to get to our vector. That's the angle I'm going to be looking for. We're going to call that angle theta. That's the regular trig direction. So what do? We start at x-axis and rotate counterclockwise. Okay, and we use this when there's no context. We're not talking about bearings or north, south, east, west, just a regular vector. So we start at the x-axis and we rotate counterclockwise. That's the direction. And we've done some of these before. So what I would do is, let's make our right triangle. So we know this side of the right triangle is negative root 3. This side of the right triangle is 1. So we could do tangent theta equals tangent is opposite over adjacent. Okay, so this is unit circle value. We need to think back to our unit circles. So remember, tangent is sine over cosine. And we would want sine to be 1/2 and cosine to be root 3 over 2, so that when we keep change flip, we get the root 3 in the denominator. Now, since we're in the second quadrant, we know that the cosine one is negative, so cosine needs to be negative root 3 over 2, sine needs to be 1/2. So we need to think about at what angle measure would that be true. We're in the second quadrant. Where would sine be 1/2 and cosine be negative root 3 over 2? Do you remember our unit circle? I bet we do. Very nice. Yes, 5 pi over 6. Well done. Okay, so there's our direction. Our direction is just regular trig direction, 5 pi over 6. Now, if we were using our calculator, we would need to be careful that whatever angle our calculator gave us was in the second quadrant, because we know calculators are fussy, right? They don't always give us the angle in the right quadrant that we want. But we would need to be sure we're in the second quadrant. Okay, we good? All right, so this is type 1. We're just going to call this regular trig directions. Okay, that's one way to find a direction. Okay, so we're going to leave direction for just a moment and just find u dot v and the angle between u and v. So we're going to practice our dot product on number 2. Okay, so u dot v is just an operation we do on vectors. So u dot v is going to be equal to, and u dot v is just a number, so we're going to match the x's up. So we're going to do 2 times 4 plus, then we're going to match the, so that's matching the x's up, 2 times 4. Then we're going to match the y's up, 5 times negative 3. So 5 times negative 3. And we're going to complete that. So it's going to give us what, 8 minus 15, or what, negative 7. So if the dot product between those two vectors is negative 7, are those vectors perpendicular to each other? No, because to be perpendicular, the dot product has to equal what? 0. It has to equal 0, and it doesn't. So these are not perpendicular. They didn't ask us that. I just wanted to reiterate, what could we learn from a dot product alone? We could learn whether the vectors are perpendicular to each other. I would like to draw these two vectors over here so we can get a kind of a feel for what we're doing. So I'm going to draw vectors in standard form. So vector u is over 2 and up 5. So like that, and we'll call this one vector u. Vector v is over 4 and down 3. It's right here. Vector v, and those are in standard position, so they are tail to tail. Our task is going to be to find, we're looking for this angle measure. The angle measure between those two vectors we would call theta. That's what the formula we're getting ready to use is going to find for us. It's going to find the angle between the two vectors. Now, we know that they're not right, they're not perpendicular to each other. Does that look to be like, I mean, provided that my graphing is okay, I mean, it's not perfect, but provided my graphing is okay, does that look to be an acute angle or an obtuse angle? It does look obtuse, doesn't it? It kind of looks obtuse. So I'm hoping when we finish this process, the angle is going to be obtuse, because that's what it looks like it is. So let's do our formula. So the formula is cosine theta equals, it's the dot u dot v, which we already found, which was negative 7, over the magnitude of u. So I'm just going to write out the magnitude would be 2 squared plus 5 squared times the magnitude of v would be 4 squared and negative 3 squared. Okay. So it's cosine, so which I like. That means that we're not going to have any funny business when we get to obtuse angles, will we? Cosine really does read obtuse angles. It's okay. When I'm going to put this in my calculator, if you recall from times past, we would arc cosine both sides. Remember that? So we could solve for theta. So theta is actually going to be the inverse cosine of negative 7 over the square root of 2 squared plus 5 squared times the square root of 4 squared plus negative 3 squared. Okay, so I'm going to pause there for just a moment so you can get that down. And then I'm going to go to my calculator and we're going to put that in the calculator. They're asking us to find it to the nearest degree. So they want us to put our angle in degrees. Okay, so just make note of whatever you're asked to do. Okay. Is everybody ready for the calculator? Not quite. I'll pause just for a moment. Okay, so let's go to our calculator. And we want to put a calculator. Okay. So we're going to go to, so I need to be sure I'm in degrees because that's what they asked me to do. They asked me to do nearest degrees. We just need to be aware, just aware, we're in degrees. So I'm going to it's trig, it's inverse cosine. I'm going to do a fraction, so control equal, I like fractions. So we got -7 over. And I'm just going to write it all out, just the square root of, just going to type it out exactly how it is. So it's what, 2 squared plus 5 squared. And then we're going to multiply that by another square root. And this is going to be 4 squared plus, now it wants me to do -3 squared. Are y'all okay if I just do 3 squared? Let's talk about that. It'd be easier for me to put 3 squared. Because if I don't put 3 squared, I'm going to have to put -3, and I'll just go ahead and do the -3 because I think that freaked out some people earlier. -3 squared. If you don't put the parentheses in the right place, you're going to get the wrong answer. And since we're squaring the number, it's going to turn out positive anyway. So you could just put 3 squared. It's not a problem. I just want you to know it's not a problem. You can do that. But that was a little disturbing earlier. So I want to make sure we're okay. So then I'm just going to do Control Enter. And here's my, so it is an obtuse angle. We were right. It's 105.068 degrees. They wanted us to do it to the nearest degree. So that would be just 105 degrees. So let's go back to our work, and let's say our theta is 105 degrees. So that's our angle between, and this is our dot product. Okay. So are we doing okay with the dot product? Those are the two kinds of things we'll see with dot product: angle between, or determining if two vectors are perpendicular. The last kind that we're going to work on is an application problem. This is where I want to go over the other two kinds of direction. So I'm going to circle this. This is regular trig direction. Regular trig direction starts at the x-axis and rotates counterclockwise. That's what regular trig direction does. And how do I know that it's regular trig direction? Because they just give me a vector in standard form and they say find the direction. They don't tell me anything. They don't like say, oh, it's a bearing of, or oh, it's north, south, east, west. None of that. Okay, so that's regular trig direction. So I want to go over here to the side and put the other two kinds up here. So bearing, so we'll call this the kind number 2, is bearings. Okay, what we do with bearings is we measure from the north line clockwise. So for bearings, we measure, this is the north line, measure from north line, and we rotate clockwise. Okay, that's what bearings, and we've done bearings before. This is when it's in a bearing form. We measure from the north line and we go rotate clockwise. So this, if I were to estimate, I don't know, maybe theta would be about don't know, 120 degrees. Oh no, I'm making it up. I don't know what it is, but it would be around that, right? Because we went past the 90-degree mark and we rotated a little bit farther. So that's bearings. Do we remember bearings? Are we okay with that? Okay. The new kind today is north, south, east, west. And this is a little bit weird, so I'm going to do one of each kind. There's 4 kinds, right? So I have northeast, northwest, southeast, southwest. I'm going to do all 4. So, okay. So here we go. So we'll do this that we have, north 30 degrees east. We'll do that one first. So this is with north, south, east, west directions. This is type number 3. Okay. So if we have north 30 degrees east, what we do is we measure from the north line, and the 30 degrees is embedded between the north line and the vector. This is north 30 degrees east. I drew my north line and I embed the angle measure between the north line and the vector. That's the 30 degrees. That's if it's northeast. Okay? Let's see what would happen if it was north 30 degrees west. Let's look at northwest. How would I do that? Okay? I have my north line. Northwest is up and left. So I draw my vector here. And that's the 30 degrees. That's north 30 degrees west. So let's talk about quadrants. So northeast is in quadrant 1. Northwest is in quadrant 2. Why do we care which quadrant it's in? Because the quadrant determines the sign of the component. And this is so important. I'm just going to write a big asterisk. The quadrant determines the sign, S-I-G-N, of X and Y components. So this is a big deal. Okay, the quadrant determines the sign of X and Y components. So if I'm in quadrant 1, X is positive, Y is positive, right? If I'm in quadrant 2, X is what? X is negative, Y is positive. And you have to note that and write it down. This is like one of the most missed things that I see students doing, is when they write their components down, their vector components, they don't write the correct sign down, whether each is positive or negative. All right, so now let's do some south. So let's do south 30 degrees east. Okay, I've got my north line here. I'm actually going to draw a south line. And so we'll just put a dot in the middle. So southeast would be down and right. That's east. So my vector would go like this, and 30 degrees would be right here, sandwiched between the south line and the vector. And what quadrant is this in? Quadrant 4. This is quadrant 4. And in quadrant 4, X is positive, Y is negative. Let's do the last one. We'll do south 30 degrees west. Okay, I'm going to draw my north line. I'm going to draw my south line. And my south is down and west is left. So I'm going to have a vector that looks like this, and the 30 degrees is going to be sandwiched between the vector and the south line. So this is our third and final way to do direction. And this lesson has some north, south, east, west notations. That's why I needed to be sure to go over this. Okay, so we've looked at all four possibilities. So what quadrant would southwest be in? Southwest. Which one? 3. Absolutely, quadrant 3. Southwest would be in quadrant 3, where x is negative and y is negative. Really important distinction for us is to determine the sign of x and y. Okay. How are we doing? So we've talked about all the different ways to do direction. That's just an extra benefit, right? Just want to make sure we all understand. Now let's do this last problem. So we have an airplane that heads due north at 300 miles per hour. It experiences a 40 mile per hour crosswind flowing in the direction north 30 degrees east. Okay. Express the velocity of the airplane relative to the air. So those are fancy words. The velocity of the airplane relative to the air and the velocity of wind in component form. It's just asking us to write those vectors in component form. That's just fancy words for how would you write the airplane vector in component form, how would you write the wind vector in component form. So I'm going to draw, let's do the airplane vector first. Airplane vector heads due north at 300 miles per hour. So I've got a vector that's going straight north, and the length is 300. Okay, that's like one of the easiest vectors to write in component form. So vector v in component form would be, am I going x, anywhere x left or right? Nope, so x is 0, and y happens to be up, so it's positive. Easy, easy. There's my component form of the airplane. And they're saying the airplane is V. Okay, so is everybody okay with the airplane one? All right. So now we need to do north 30 degrees east. And I don't know, I'll try to copy and paste it. Okay, I'll just put it, where should we put it? I'll put it over right here. No, I didn't like it. Okay, we'll just draw it. Okay, so here we go. We're going to do the wind now. So the wind is north 30 degrees east. So I'm going to draw it up here. So here's my north line, northeast. So it's going like this, 30 degrees. Okay, so I'm in a coordinate plane. So I'm going to drop to make my triangle right here. So I'm just going to find my x component and my y component. We've done that before, but I really would prefer to deal with the angle inside the triangle, not the angle outside the triangle. And we know that that pair is going to be a sum of 90, right? So I know that this angle would be 60 degrees. Okay, so then we can do cosine of 60 degrees equals adjacent, which is x, over, and let's see, our magnitude is 40, so this is a length of 40, over hypotenuse, which is 40. So x is going to be 40 cosine of 60 degrees. We know 60 degrees, cosine of 60 degrees is a half, so it's 40 times a half. So my x component is 20. So let's start. So vector u x component of 20. Okay, so we're just using right triangle trig. Is everybody okay? Okay. So now I want to find the y component. I want to find that height. So we'll do sine of 60 degrees equals opposite, which is y, over hypotenuse, which is 40. So y is going to equal 40 sine of 60 degrees. We know sine of 60 degrees is, root 3 over 2. So 40 times root 3 over 2, which gives us, what, 20 root 3. So our y component is 20 root 3. So we just have finished part A, where they asked us to write the two vectors in component form with fancy words that seem confusing. But it really just means write the vectors in component form. Okay. Are we okay? Okay, good. So part B, find the true velocity of the airplane as a vector. So I need to give you a definition. True velocity equals airplane velocity plus wind velocity. Just add them together. If we're doing boats, because they like doing those too, it would be boat velocity plus what do you think affects a boat? Currents, exactly. It would be boat velocity plus current velocity if we're doing boats. Those are the two main ones, is airplanes and boats. Okay? So let's do what they asked. We're going to find the true velocity. True velocity is a vector. True velocity is a vector. We're adding two vectors together, which we know how to do that. And they like to use the Greek letter omega for true velocity. I really don't know why, but they like it, so that's what we'll do. So 0 plus 20 is 20. 300 plus 20 root 3 is 300 plus 20 root 3. I'm not going to try to give a decimal approximation for that. That's our true velocity. Okay. True speed. I'll give you another definition. True speed equals the magnitude of true velocity. And I promise you, if you know what these words mean, you will have no trouble doing what it asks. But if you don't remember what they mean, it's going to be very difficult. So these are vocab words. You need to understand what they mean. True velocity is the airplane velocity plus the wind velocity if you're doing airplanes. If you're doing boats, it's the boat velocity plus the current velocity. True speed is the magnitude of true velocity, period. True speed is a number. True speed is a number. It's like how fast you're going. Now I want us to think about this before I calculate it. So it says that the airplane is heading due north at 300 miles per hour. And we have a wind that's flowing northeast. Do you think that's going to speed the plane up or slow it down? It's going to affect it. If the plane is going north and the wind is going northeast, do you think it's going to help the plane move faster or hurt it? It's going to help it, isn't it? Because it's going kind of a north direction. So we should expect our true speed to be greater than 300. Okay? So we'll find that. That's the magnitude. So the magnitude of our true velocity is the square root of 20 squared plus 300 plus 20 root 3 squared. And I did go ahead and put that. I think y'all are good with radicals in the calculator, so I'm not going to pull the calculator up. The true speed is 335.237 miles per hour. So we were correct in our observation that we thought that would help the plane go faster, because the plane was actually heading due north at 300 miles per hour, but it's really going a little faster than that because of the wind. What do you think that would happen if the wind was going southeast? It would slow it down, right? Because the wind would be going against it. Think of it as a vector. It would be pushing against it. But in this case, it's going with it. So that's our true speed. The direction of the plane. Okay, let's write this out. Direction. We want to use same from what you were given. You know, we have three choices of how to do direction, right? We have three choices. We could do it as regular trig, we could do it as bearings, or we could do it as north, south, east, west. How did they give us the information? North, south, east, west. So that's how we need to give it back. This is important for us. How to write our direction. We have to use what we got. We're in north, south, east, west. We have to give north, south, east, west. So how do we find the true direction? I would tell you the very easiest way. Of course, I'm all about telling you the very easiest way. What we're going to do is we're going to graph the true velocity vector. So x is like 20 and y is like 300 plus 20 root 3. So here's my vector right here. And so my direction, what I want is right here. Right? That's my direction, because we'd have to do north, south, east, west business. I want that angle, but I really need to do a little bit of work to get that angle, because I need to use this triangle, this right triangle. So I'm going to call this angle A. I'm going to find angle A inside the triangle. So we know this is 20 this way, and this is 300 plus 20 root 3. So we're going to use tangent A equals opposite, which is 300 plus 20 root 3 over adjacent. Again, we've already gone through this calculation. So I'm just going to tell you, when I put it in my calculator, this is the angle I got, 86.5797 blah, blah, blah degrees. Is that the angle measurement that I want to use? No, that's the angle measurement for A. I need theta. What should I do to find theta? What should I do to find theta?
Do 90 minus.
Absolutely, you're exactly right. 90 minus. So theta is going to be 90 minus 86.5797 degrees. And so theta turns out to be 3.420 degrees. So let's get it written properly. We need it to look, you know, like this right here. Oops. Come on. We need it to look like this. Right? That's how they look. So that's still northeast, isn't it? It's in the first quadrant. That's still northeast. So we would say north 3.420 degrees east. That's our direction. And we're using north, south, east, west notation because that's what they gave us. Okay?